Hi everybody, this is Jeff Mankowski. Welcome back to the Maverick Statistics channel. In the last video, we did an introduction to the empirical rule, and in this video, we're going to do a deeper dive. What we're going to talk about is what you do when you have a data set, you know it's bell-shaped, and you're starting to see very, very high or very, very low values in the data set. Like maybe you notice a number that's so low, you're saying this number must be a mistake. It's so low compared to all the others, I'm just going to delete it. Now, is it okay to do that? Can we just delete an observation that looks like it doesn't belong there? That's exactly the kind of question that we're going to ask in this video. And we're talking about it because in statistics, we have these things called outliers, which are extremely high and extremely low values in the data set. And we need to know, should we leave them in the data? Should we take them out of the data set? What do we do? So we're going to learn how to find out how far away is far enough from the mean to label a value as an outlier, and then how do we make that action call to know what to do? As a statistician, these are all really important things that we need to know about. Now, what we're also going to do is we're going to generalize by the end of the example we're going to work with to something called z-scores and standardization. And z-scores are hugely important for Statistics 101 class. We use them continuously throughout the semester, so lots of important content coming up. And what we're going to do is work with an example from the last video that had to do with flights from New York City to Miami. So if you haven't seen that example, you might want to take a look at the last video. And to start with, what we're going to do is we're going to write in a couple more important items that we know from the empirical rule, and then we're going to get to work. So here we go. We're going to write in okay, so if we find an observation and that observation is located 2 or more standard deviations from the mean, it's unusual. That means it's unusually high or it's unusually low. So we're starting to get into the extremes of the data set. Now, if that's 2 or more standard deviations, what happens when you find a value that's even further away? Okay, so if it's 3 or more values away from the mean, that is not values, 3 or more standard deviations from the mean, it's a more serious situation. Of course, we're going to call that an outlier. So if you've identified an outlier, what do you do with it? Do you leave it in the data set or do you take it out of the data set? Probably the best thing that you can do is just investigate for starters. Just find out, how did that observation get there? Was it a mistake? Was the measuring instrument wrong? Did it give you a wrong number to alert, and that alerted you that there's something wrong with the experiment? Because we need to find out if that value is legitimate or not. Now, once you have that intel, then you can make the call on whether you're going to leave that in or you're going to remove it from the data set. So to get a practical example from this, let's go ahead and turn our attention to the last example that we did. And let's write in a question here. We're going to say, suppose a flight from New York City to Miami lasted 155 minutes. Would it be considered? Okay, so 155-minute flight. Is that flight going to be considered an outlier? And the really fast way to answer the question is, from the last video, we happen to know already that 99% of our flights are going to last between 90 minutes and 150 minutes. And we know that because the empirical rule told us that we're going to find 99% of the data in the data set when we go 3 standard deviations below the mean and 3 standard deviations above the mean. And remember that 3 standard deviations is going to tell us that we need to move 3 units of 10 because our standard deviation is a 10, which they gave us in the exercise. So what we're going to do now is we're going to take that 155 minutes, we're going to compare it to the 150, and we're going to say, okay, are we above that break where 150 is? And of course, we know that 155 is larger than 150, so our answer right away is going to be yes, that number is definitely going to be considered an outlier. Let's go ahead and write in our answer here. We'll erase this. We're going to say yes. We'll put in 155 is an outlier. Okay, now that we know that, let's go ahead and let's think about a slightly more challenging question. Exactly how many standard deviations is 155 from the mean? So let's go ahead, let's kind of write in what we're thinking about here. We're going to say exactly. Okay, now what we can do to kind of get to the answer quickly if we want, we can say we know that when we hit this 150 right here, we were 3 standard deviations above the mean. So we know we have to be at least 3. And when we go from 150 to 155, how many more standard deviations did we just travel? Well, from the exercise, or from what's given in the problem, we were told that the standard deviation is 10 minutes. So that must mean the difference between 150 to 155 is going to be exactly equal to half a standard deviation. So our answer is going to be, let's write in 3.5 standard deviations. Okay, so now that we know it's 3.5 standard deviations, the next challenge for us is to say, what if I'm on a test and I only have a minute on the clock? Is there a way that I can find the answer without going through the whole computation of finding out first where's 99% of the data? In other words, is there a formula that can get me this answer much more quickly? The answer is absolutely, there is a formula. Let's go ahead and let's talk about mechanics for a little bit. Originally, when we were trying to say how many standard deviations is 155 from the mean, what we really needed to do was say how far is our observation from the mean and get that answer in terms of standard deviations. So when it comes to the computations, the mechanics, here's what it looks like when we translate that into a numerical formula. We know we started with 155, just like so, and we were saying, how far is 155 from the average? We know from the problem that the average is 120 minutes. So we needed that distance in terms of standard deviation. So we take the difference between 155 and 120, and we're going to divide that by 10. And that's going to give us exactly 3.5. Now, once we have that, our 155, our 120, our 10, and the division sign, can we generalize that even more into a formula? And the answer is absolutely. So here we go. We could have asked the same question, didn't have to be for 155. It could have been like a flight for 160 minutes, 170 minutes. So what do we do when we have any given number? We're going to call that 155 our x value. In terms of formulas, we already know from some of the previous videos that 120 is our mean, and the symbol for our mean is going to be the mu. In this case, we're going to be using the symbol for the population average. Now on the bottom, the 10 is our standard deviation. So what's our symbol for that 10? For the standard deviation, and that's going to be a sigma. And this formula right here is going to be what we call our z-score. So we're going to go ahead and we're going to write in our z formula. And this right here is one of our most important formulas that we're going to use in our statistics class, because we end up using z-scores for anything. Not anything, should say, for so many different things throughout the course. Lots of them always kind of collapse down to standardization. So what we'll do is we're also going to go ahead in the formula and we're going to write in, this is something that I just find helpful, a little subscript of 155, just to indicate that we standardized a score of 155. Now, in case you're wondering, what would you do if you needed to use the symbols for a sample, because it turned out somebody wrote somewhere in the exercise that all this information had to do with a sample. And the answer is, well, we would switch out the formula. We would take the counterparts for sample and switch that for the symbols for a population. And let's just write in little notes here. We're going to say using population data. So what would this thing look like if all the data was from a sample? In this exercise, it wasn't really specified, so we kind of took the liberty of assuming that it was from a population. Right down here, we're going to say using sample data. And off to the left, we're going to write in, we would still use the Z formula, meaning the notation for Z exactly like it was looking before. I'm going to attach a little subscript for the 155. What our formula is going to do is it's going to have our X sitting there. Instead of the mu, we're going to put in what our symbol is for sample mean, which is going to be an X bar. And on the denominator here, instead of sigma, we're going to use our standard deviation for S, which is the standard deviation of a sample. And over here, our numbers are going to look exactly the same. That won't change at all. It'll still read 155 minus 120. And then we're going to come around and we're going to divide by 10. And that's still, again, going to equal exactly the same value it would before, which is going to be, let's do that in the right color here. That's going to be a 3.5. Okay, so now what's really cool about this is now that we know these formulas here, I'm just going to put these in a takeaway box for us. Now that we know our standardization, our z-score formulas, what we can do is we can go to any observation in a data set. In fact, we can go through all the observations and we can start stamping, okay, which ones are unusual, which ones are outliers, which ones are not unusual, which ones are not outliers, because we can use the z-score on any different observation. And now we know exactly how to figure out which are unusual and which are outlier, because we know exactly what standard deviation distances go with each category. I'll see you on the next video, and thank you for watching. This is Jeff Mankowski with Maverick Statistics.